Okay, so how do we solve this model? How do we analyze it? Let's go on to the next page. From the point of view of the social planner. So, the social planner wants to maximize Z, okay, which was Y minus costs. So that's actually just C, isn't it? I don't know why I didn't call it C. Whatever. Z is ALL to the 1 minus alpha, and then instead of R we can write that sum over J of dj all to the alpha times e to the minus p to the phi, but p is just the sum over j of psi j dj all to the phi minus the sum over j of wj dj. That's costs, yeah? So to solve this, we need to take first order conditions. If we take the first order condition in D1, what do we get? Okay, so remember this is y. So dz, let's do this steady. dz dd1 is dy dt1 minus this, which is just whenever it's some d other than d1, the differential is just 0, right? So this is a series of terms, and for one of these we get w1. For the others we just get zeros, yeah? So that's this. And what is dy dd1? So remember this is r, yeah? R to the alpha. So dy dd1 is dy dr dr dd1. Okay, that's the chain rule. Plus the differential with respect to this. So we can think of that as dy dp dp dd1 minus w1. Okay. So what is dy dr? It's alpha times y over r. Okay, and what is dr dd1? R is just this sum, so dr dd1 is just 1. Okay, so that is the first term. What about the second term? What is dy dp? So p is this sum, right? So it's e to the minus p to the phi. What's the differential of that? It turns out it's actually sorry, let me just pause this and think about the best way to explain it. Okay, I think this is playing now. Yeah, okay. So this is playing. I think what I'm going to do is actually say, in an aside, to explain this, I think let's say x, so I'm defining something new which I call x, is the sum over j of psi j dj all to the phi. So then e to the that, we can write e to the minus blah 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 to the phi, we can write as e to the minus x. Okay, so that's just the definition. So then I can say that actually dy by dp is the same as dy by dx by dp, and then we've still got dp by dd1, and we still got minus w1. So when we go to the next stage, dy by dx, we've got e to the minus x. So you all know, well, dy by dx is minus y. Okay? dx by dp, x is p to the phi, so dx by dp is phi p to the phi minus 1. Or was that phi or psi? Yeah, it's phi, yeah. So dx by dp is phi p to the phi minus 1. And finally, dp by dd1 from the definition of p is just psi 1. Okay, so we end up with that. Phi psi 1 p to the phi minus 1 y. Okay, equals 0. So when we rearrange for an internal optimum, we need that alpha y over r is phi psi 1 p to the phi minus 1 y plus w1. Okay. And by symmetry, we can write down the symmetric expression for the first order condition in D2, which is going to tell us that alpha y over r is phi psi 2 p to the phi minus 1 y plus w2. Okay. So these two expressions in the first order conditions in the technology 1 and technology 2, or resource 1, resource 2, the left hand sides are the same. That's the marginal benefit of using more resource. The right hand sides are different. That's the marginal cost, which is the pollution cost plus the extraction cost. Okay, so what happens? Imagine that we've got a resource which is both cheaper and cleaner. So W1 is less than W2, Psi1 is less than Psi2. Then, intuitively, we know we're never going to use, they're perfect substitutes, right? So we're always going to choose one or the other unless they're perfectly balanced. But they're not perfectly balanced. This one is better, so we're never going to use this one. So this one will not hold because we'll be at a corner where D2 is 0. This one will hold. And when this one holds, we can start looking at the special cases. Basically, yeah, what do I want to, this is getting into a long video here. How much do I want to talk about this? Okay, so we've only got one input that we ever use, and this is the equation telling us how much we use. What is that now telling us? Okay, So we've got this equation. What is it telling us? In general, it's a little bit complicated, okay. But at the extremes, we can say it simplifies. Okay, we can say more simpler things. So let's assume the extreme, it's a bit like the previous model with the like primitive economy and the highly developed economy, right? One we looked at a couple of lectures ago. So let's look at a primitive economy when productivity is very, very low. Okay, so we're thinking about productivity AL growing over time, remember? And we go back a long way in time, productivity is very low. Then we know for sure that Y will be low and R will be low. Whatever happens, we just cannot extract much resource, we cannot produce much. Okay? But this probably won't be low, yeah, because it's the ratio of two small quantities. It's not necessarily low. But P is directly linked to R, right? So this is definitely low. Phi, by the way, has to be greater than 1. So this is definitely super low. This we don't know, and this is just a number. So basically, so this is not super low, this is. So basically, early on, this one is negligible, and we have alpha y is W1R. Oh, it's just that super familiar result. The resource share is alpha, and it's the price, the extraction cost per unit of resource times R. Very simple. There's no pollution tax. In the limit of very low productivity, we don't tax pollution because the costs of pollution are so low, we're very poor. Okay, now let AL be high. Let AL be very high. Okay, then presumably Y will be high. R we're not so sure about because R causes pollution, but presumably if we're very productive, we'll have a lot of production. So now we know that Y is high and P we're not sure about. Remember, this is the extraction cost, this is the damage cost. Basically, if Y is going through the roof and P might not be going to 0, this is likely to get big. Okay. And what happens is that this does get big compared to this, and we can ignore this instead of earlier ignoring this. So now we have alpha Y over R is phi psi 1 P to the phi minus 1 Y. And those go out. And remember, R is just D1, yeah, because we've only got one resource. So we have alpha over D1 is phi psi 1 D1 to the phi minus 1. So if we bring this D1 up, we can wipe that and wipe that minus 1. And we have D1 to the phi is this. Oh, sorry, I think I got that wrong, didn't I? I think it should be like that. I think throughout we should have had that. It doesn't really change anything. Oh, no. It's like psi 1. Oh, it should be psi 1 to the phi. Alright, I gotta pause this video. Right, Sorry, got myself into a tangle there. It was all correct until the end here. It's phi psi 1 times p to the phi minus 1, and p is psi 1 d1 to the phi minus 1. Then when we bring this up, we end up with alpha is phi psi 1 d1 to the phi, and that's just p, so we end up with p is alpha over phi to the 1 over phi. And this is just constant. So basically, what happens is that over time, or actually from 0 very early on, y grows like this, and p grows like that. And it's a little bit like, so this is, if we go back to DHSS, this is like the unlimited resource costly to extract, and this is like land. The price tracks GDP, the quantity stays constant. Here the price is constant and the quantity tracks GDP. So that's when we don't have an alternative resource. But what about when we do have an alternative resource? We'll look at that in the next video.